excellent times the hits of poor divided by hits of phrase near poor times hits excellent. Okay, and then you are calculating the log of it. I'll pause here. Do let me know if this part of the formula is okay to everyone. Let me know if it is not okay as well. I will be again happy to explain this part to you.
What is meaning by near and hit?
Near and
Near and hits.
hits is basically the number of times it's appearing. So for
Near?
this experiment, right? Yeah, near is the index, meaning that um, how near the words are. So if a particular word is two words near to excellent or one word near to excellent, so how near a particular phrase is to the word excellent. So it's giving you an index basically. So you have the movie was excellent, right? So you have the term excellent and you are trying to calculate how far, I mean, the term is from the phrase the movie. Okay, so you are trying to find out that how many times the movie is appearing near to the term excellent. So you can define when you are saying near, you can define whether this near means two words near, three words near, four words near, or what.
So the near is meaning that we have keyword like excellent. So we are finding some keyword how many so-called character is in between from the keyword until the excellent.
No. So you are telling that for me, near means that any word which is three words near to excellent means near. And if your phrase is the movie, right? So you are trying to find out how many times the movie is appearing three words near to excellent or two near to excellent or one word near to excellent. Nothing beyond that. Because you might not always get the movie excellent together, right? You might not always. So you are defining that it can be slightly far as well, but still I'll consider that to be near. It might not be consecutively appearing, but it might be one to two words here and there, and I am accepting that.
Okay, a quick example, the sentence that you given is the movie was excellent. So you
Yeah.
say the near is three because the movie was is three, correct?
Yeah. So three means that there can be three words in between. There can be one word, there can be two words in between, there can be three words in between. Still, they will be considered near.
Okay, so I quote it as example, the movie was excellent. Okay, if the movie was very, very excellent,
Still, it is near.
it still is considered near.
Correct.
So what is the condition that we never hit the near?
Yeah. So that
Extreme.
condition depends on you, right? You can define that how you are accepting that nearity.
Oh,
For
okay.
your data, it is like two or three or four. So you can define that.
Okay, meaning I quote an example, maybe I say uh, the definition of near I said is after five work is not considered near.
Correct. Correct.
Oh, okay. How about hit?
Okay.
Hits.
Hit is the count, basically. Count. Number of times it's appearing.
Oh, okay, understand.
Yeah. All right. Okay. So it has been seen Again, this is an experiment that is being performed already by somebody, right? So it's been seen that words like online service, so you can see that there's an adjective and there's a noun, has a polarity of 2.8. Online experience has a polarity of 2.3. Direct deposit has a polarity of 1.3. Local branch 0.42. So likewise, for many such phrases, there are some positive polarity, there are some negative polarity, and if you take the average of it, this particular um, what do I say, collection of items has an overall positive polarity. So from this, if there are phrases like online service, online experience, or low fees or true service, then such words has a positive impact in the prediction of the class itself. Okay, from the same experiment, for phrases like uh, direct deposit, virtual monopoly, less, you can see that some are positive, some are negative, but again, if we are taking the entire average of it, it is giving us negative polarity. All right, so it's from the experiment itself. And this experiment, or this algorithm, this Tourney algorithm, right? Or Tourney algorithm, as you may call it, can be useful for us to get new phrases and define its polarity, define polarity of new phrases as well. Okay, and we have seen how it is calculated, how the formula is calculated, and so on. So the result of Tourney algorithm was that out of 410 reviews from opinions, 170 were negative and 240 were positive. And it was far improved than majority of the baseline algorithms, which stands at 59%. This Turney algorithm seemed to give around 70%, 74% accuracy in terms, sorry, in terms of accuracy itself. Okay, so 74% score in terms of accuracy. So in a nutshell, the Turney algorithm is not using individual words, but it is using phrases. And this gives us some information about the uh, domain specific information as well. Okay. Next, using the WordNet to learn polarity. So WordNet is an online thesaurus where again it contains a lot of like such words and phrases and sentences, right? So from this, create positive and negative seed words, and again this was manually labeled, and the WordNet polarity, right, uses, so what it does is that there are a few set of positive words and negative words. Okay, the WordNet is expanding. So what people are doing here is that in the positive set, it is adding synonyms of positive words. So for example, for the word maybe good, right, we are adding synonyms in the positive set like well and so on, and we are adding the antonyms of negative words. So synonyms of the positive words and antonyms of the negative words are being added to the positive set. To the negative set, we are adding the synonyms of the negative words like awful and antonyms of the positive words like evil, and we are repeating this following chain of synonyms as an as and when required. So this is a set of lexicons, right? So it's WordNet, which is set of lexicons that are there. From here on, if you want to train your model based on these lexicons, you can filter out the data and take certain data that you want. But that's the reason WordNet is still expanding. So, in a summary, on the learning lexicons, some of the advantages and disadvantages can be like it can be domain specific, and new words can come up, right? So, with lexicons, you can make a more robust model, and we have seen certain algorithms that uses the similarity index and then try to come up with the phrases itself. It doesn't consider the individual words and so on. And the intuition is that you start with a seed set of words, right? You say a good, and then you find other words that have similar polarity. And this can be done using and but. So if two words are used using and, then they are similar. If it is used using but, they are dissimilar. It can be done using words that occur nearby in the same document. You can define that nearby, how near it is. Using the wordnet synonyms and antonyms, we have seen that in the wordnet you can have antonyms of certain words, putting into the opposite polarity, synonyms putting into the same polarity, and so on. Use seeds and semi supervised learning to induce lexicons as well. So that's the end of this particular chapter. Okay, so I'll quickly share the video as well, so for some additional info if I have missed out any. So let me bring up the screen.
That there are sentiment lexicons available. For lots of other purposes, we'd like to build our own sentiment lexicon. And the way we do this is often by semi-supervised learning. And the idea of semi-supervised learning is we have some small amount of information. Maybe we have a few labeled examples, or maybe we have a few hand-built patterns. And from that set of data, we'd like to bootstrap a complete lexicon. And we might want to do learning of lexicons instead of taking an online lexicon if we're looking at a particular domain that maybe doesn't match the domain of the lexicon that was built, or we're trying to do a particular task, or maybe we just think that our online lexicons might not have enough words that are relevant to the topic we're looking at. One of the earliest ways of inducing this kind of sentiment lexicon was proposed in 1997 by Hatzivatsaloglu and McEwen, and I'm going to show you this because although the paper is old, this intuition is included in almost all modern ways of doing this semi-supervised learning of getting a lexicon. And their intuition, very simple, is that two adjectives, if they're conjoined by the word and, they probably have the same polarity, and if they're conjoined by the word but, they don't. So if you see on a very high frequency of fair and legitimate or corrupt and brutal, probably fair and legitimate are both on the same polarity. And so we might suspect that fair and brutal are just less likely to occur on the web or in some corpus. And so if we see a lot of something occurring with and, maybe the two are likely to have this. But if we see two words linked by but, they probably have different sentiments. So fair but brutal more likely to occur than fair and brutal. And here's how they used this intuition. They first labeled by hand a seed set of 1,300 adjectives. And so they had about a similar number of positive and negative adjectives, so central or clever or famous or thriving, and negative adjectives like ignorant or listless or unresolved. And now from the seed set, they expand that to any adjective that's conjoined with a word in their seed set. So for example, we can go to Google and we can type in was nice and look at what words occur next. And what do we see after was nice and? Well, we see was nice and helpful. So that tells us that nice and helpful are likely to have the same sentiment. And here we see nice and classy. So that tells us that nice and classy might have the same sentiment. And we can do that for all sorts of words that occur conjoined with our seed set, and we take any word that occurs frequently enough in the right conjunction with our seed set words. And now we can build from that a classifier, and the job of the classifier is just to so we can give the classifier the count of the two words occurring with an and in between them, and a count of the two words occurring with a but in between them. And the classifier can learn that nice and helpful are somewhat similar, nice and fair are very similar, fair and corrupt are very dissimilar. I've marked them in red with a dotted line, because maybe but occurs much more often between these two, and occurs more often between these two, and so on. So we can get between any pair of words a number that indicates its similarity. And now we can just cluster the graph and use any kind of clustering algorithm. And we get, for the words that tend to be linked together, helpful and nice and fair and classy, we'll get that these are linked together, and brutal and corrupt. And our output polarity lexicon, and here I've shown you an output polarity lexicon, and of course it'll have some mistakes in it. So see if you can find the mistakes in this lexicon. Here are some of the mistakes. So we have disturbing as a positive word, or strange as a positive word, or pleasant as a negative word. So of course there's going to be errors in any of these kind of automatic semi-supervised algorithms. So while the Hatzavasa-Loglu and McEwen algorithm automatically finds the sentiment or the polarity of individual words, it doesn't do well with phrases, and we'd like often to get phrases as well as words. So the Turney algorithm is another way to bootstrap in a semi-supervised way a lexicon. What this does is extract a bunch of phrases from reviews, learn the polarity of the reviews, and then take all the phrases that occur in a review, take their average polarity, and use that to rate the review. So let's look at these stages in the Turney algorithm. First, we're going to extract every two-word phrase that has a particular set of part of speech tag. And we haven't talked about parts of speech yet, but so this is adjective, the tag for adjectives. So if the first word is an adjective, and the second word, this means noun, and this means plural noun. So if the first word is an adjective, so an adjective followed by a noun or a plural noun, we'll extract that phrase, whatever the third word is. Or if the first word is an adverb, RB means adverb, and the second word is an adjective, and the last word is not a noun, we'll extract that phrase. So adverb, adjective, 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 noun, adjective, adverb, verb. So these are particular phrases. So we're going to run our part of speech tagger. We'll talk about that in a few lectures, and assign for each word a part of speech, adjective, noun, and so on. And then we'll extract. The word is this tag. The third word has some constraint so that we don't extract it. And now we look at all those phrases. And our goal is, for each of those phrases we've extracted, to measure its polarity. So how positive or negative is a particular phrase. And the intuition of the Turney algorithm is, just like the Hatzavasa-Loglu and McEwen algorithm, to think about co-occurrence. So we ask, well, a phrase is positive if it co-occurs a lot nearby, let's say on the web, or some large corpus with the word excellent. A negative phrase is likely to co-occur more often with a word like poor. So how are we going to measure this co-occurrence? The standard way to measure this kind of co-occurrence is by point-wise mutual information. Point-wise mutual information. And that's a variant of a standard information theoretic measure called mutual information. The mutual information between two random variables is the sum over all the values the two variables can take of the joint probability of the two times the log of the joint over the individual probabilities. So point-wise mutual information takes this intuition from mutual information and just asks a very simple, computes a very simple ratio. The probability of two events, x and y, divided by the product of the individual probabilities. So what point-wise mutual information is asking, it's a ratio, is how much more do two events, x and y, co-occur than if they were independent. If they were independent, they would have these independent multiplied probabilities, and how much does the joint occur more often than we'd expect from independence? That's the intuition of pointwise mutual information. So looking at pointwise mutual information, I've just repeated the equation here. We can look at it between two words. We say, how much more do these two words, word 1 and word 2, co-occur than if they were independent by taking the ratio, the probability of the two words occurring together, divided by the probability of each word separately and multiplied, and we take the log of that. How do we estimate this? Well, the way Turney did it originally is by using the AltaVista search engine. And we're going to estimate the probability of a word just by how many hits we see for that word. And we're going to estimate the probability of two words by how often word 1 occurs near word 2. So AltaVista has the near operator that lets us check if a word is near another word. And in each case, we're going to want to normalize to get a real probability from these counts. And by our definition from the previous slide, pointwise mutual information, it's the probability of the joint, so that's hits of word 1 near word 2 over n squared, divided by hits of word 1 over n over hits of word n2 over n, and these n's are going to cancel, and we're going to end up simply with this equation. So how many times do the words occur near each other? How many times do they occur individually, multiplied together? So once we have a measure of co-occurrence, of how much a phrase co-occurs with the word excellent or the word good, we can now determine its polarity. So the equation for polarity in the Turney algorithm is just how much is the mutual information, the pointwise mutual information of any phrase with the word excellent, and we subtract its mutual information with the phrase poor. So how much more does the phrase appear with excellent than poor, or vice versa? And just doing a little algebra. So that's the number of, here's the definition of pointwise mutual information of a phrase with excellent, how often it occurs near the word excellent, divided by the individual number of hits of the phrase itself in excellent, and then subtract the same thing for poor. And of course, by the definition of logs, we can bring things inside the log and turn the minus into a divide. And then we can do some messing with terms. So we have hits of phrase here, and we have hits of phrase there. And so in the end, we can get our formula for deciding the polarity of a phrase. It's just how many times does the phrase occur near excellent times how many times it occurs with the word poor occurs, over how many times the phrase occurs near poor, over how many times excellent occurs. So these are constants that we can get once, and then for each phrase we can compute these two quantities. And using the Turney algorithm, here's a positive review, obviously of a bank. And so here's a phrase like online service, adjective, noun, phrase. And here's the polarity assigned by it, 2.8. Here's another one, direct deposit, 1.3. And here's some negative phrases with negative polarity. So the phrases occur more often near the word poor than near the word excellent. So inconveniently located has a negative polarity. So on average, though, more, I've just shown you a subset, more of the positive phrases occur in this review than the negative phrases, and the average polarity is positive. So this is a thumbs up review. A thumbs down review, you can see that phrases like virtual monopoly, negative polarity, lesser evil, negative polarity, other problems, negative polarity, all occur more frequently and on average have a more negative polarity than the positive polarity words that occur in this review, and we end up with a review that has an average negative polarity. So the Turney algorithm was evaluated on various kinds of review sites and does a better job than just the majority class baseline at predicting the polarity of a review. So what's important about the Turney algorithm is that it lets us look at phrases, learn phrases rather than just words. And what's true about in general about these unsupervised algorithms is we can learn domain-specific information that might not be in some online dictionary. So if I go back to the previous slide, if we're doing banking, a word like direct deposit or virtual monopoly might not be in an online polarity dictionary or online web So we need to use some of these semi-supervised algorithms for learning the polarity of these kind of words. Finally, I'll mention briefly a third algorithm for learning polarity, and this uses WordNet. Again, that's the online thesaurus that we'll talk about in detail later. And the intuition of using these online thesauruses is similar to what we've seen in the first two semi-supervised algorithms. We'll start with a positive seed set and a negative seed set. So we might have words like good in the positive seed set and terrible in the negative seed set. And now we use the thesaurus just very simply to find synonyms and antonyms. So we add synonyms of positive words like well and antonyms of negative words to the positive set. Synonyms of all those words, so maybe awful is a synonym of terrible. And antonyms of our positive words repeat, and the sets grow as we keep adding synonyms and antonyms to it. And then each of the algorithms that make use of WordNet for learning polarity will have various ways of filtering but we might be able to learn it from the web or from the data we're looking at. And again, the intuition of all these algorithms is really the same. We start with some seed set. We find other words that have similar polarity to that seed set in some semi-automatic way. And the ways we've seen are using whether the words are conjoined with and or but, using words that just occur nearby to words like poor or excellent. So that's our seed set there, or using WordNet synonyms or antonyms.
Okay, so the next one is also a continuation of this. So please have a look on the next video as well.
There are other sentiment tasks than just simple positive or negative polarity. One important one has to do with finding the sentiment of an individual sentence, which we're going to want to do for finding aspects or attributes that we talked about earlier. So that's finding the target of the sentiment, what it is that we're talking about the sentiment about. So here's a sentence: the food was great, but the service was awful. This whole sentence doesn't really have a sentiment. It has a positive sentiment about food and a negative sentiment about service. So we'd like to be able to deal with this kind of micro sentiment where we have a sentiment about one attribute and a different sentiment about a different attribute or aspect. So how are we going to find the aspect or attribute, or sometimes it's called target, of a sentiment? And I'll show you an example that a way of doing things that was developed both by Hu and Liu and by Blair Goldenson et al. And the idea is we first look through all the reviews and we find every highly frequent phrase. So let's say that the word fish tacos occurs a lot in this particular restaurant reviews of this restaurant. And then we mark down, we have filters that say we prefer highly frequent phrases if they occur right after a sentiment word. So maybe we very often see the phrase great followed by fish tacos, or terrible followed by fish tacos. That suggests that fish tacos is an aspect, a likely aspect of let's say a taqueria. So if we see great food a lot, if we see food occurring very often in a review, and we see the word great and terrible and awful before it a lot, we know it's probably an aspect that people are applying sentiment for. And this can be used automatically to find sentiment for lots of things. So Blair Goldenson et al. Used it, for example, for casino reviews of casinos to find words like casino, buffet, pool, resort, and beds are the kind of things people comment about in reviews on casinos. For a barber, you might talk about the experience or how good a job it was, or facts about the haircut. For a department store, you might talk about sales or different departments or the selection of the store, things like that. So we can automatically find the aspect. In other cases, though, the word that describes the aspect may not be in the sentence. And so for some sentiment topics like restaurants or hotels, it's pretty well understood what the aspects are that people care about for restaurants. For restaurants, they tend to care about food, decor, service, value. And so for cases where we know in advance what the frequent aspects are, here we can take a small corpus of restaurant reviews and we can hand label it. We'll just mark every sentence. Does this sentence talk about the food? Does it talk about the decor? Or is it none of the above? And then we can just build a classifier which, given the sentence, assigns an aspect to the sentence. Is this sentence about food? Is this sentence about decor? Sentence about service, and so on. And it could be a sentence, or we could assign that with, with phrases, or maybe with clauses, with pieces of sentences, whichever we'd like to do. So 2 ways of finding aspect of a sentiment. We can automatically find frequent phrases, so we can find phrases. And then we can build up a set of phrases that occur frequently and decide those are good phrases that we'd like to know about for this particular product. Or we can decide the aspects in advance. Aspects are come in advance, like we know what they are for restaurants. And then our job is just to build a little classifier to find them in the review so we can decide if what person said about the food was positive or negative. So putting this all together, this is the Blair-Goldenson algorithm from Google. We have a set of reviews. We're going to extract a bunch of sentences or phrases. So here's our extracted sentences or phrases. And now for each one of them, we're going to run our sentiment classifier. Is this phrase positive, negative, or maybe it's neutral? Okay. And then for the ones that have sentiment in them, the ones that are positive or negative, so now we have sentiments and phrases with sentiment, plus, minus, minus, plus, plus, minus, and so on. We're going to extract the aspects of these. So is this about food? Is it about decor? What's the sentence about? And so now we have plus food, and now we have minus decor, minus service, and so on. For each sentence or phrase, we have both a sentiment and an aspect. And now we aggregate these together and produce a final summary. And here's an example of what you might get as the final summary. So maybe for a hotel, for rooms, we might get that this sentence, the room was clean and everything worked fine, positive sentiment, another positive sentiment. Here's an example of negative sentiment. So we first figure out that worst is a negative sentiment, and then we might extract from somewhere in here that there's some mention of rooms. And similarly for service, we might see service gives new meaning to slow, and that's negative. We made some simplifications in the baseline method we gave for sentiment classification. We assumed that the classes, positive and negative, occurred with equal frequency. And that's, of course, not usually true in the real world. And it turns out that when the classes are not balanced, we can't use accuracies as an evaluation, and the F-score can deal well when evaluating classes where there's many more positive than negative, or maybe there's many more negative than positive reviews. It turns out that if there's a severe imbalance in class frequencies, that can actually degrade the classifier performance. And there are 2 standard things we do to deal with that. One is we just resample before we train. So for example, if one class has 1 million reviews and one class has 10,000 reviews, then we might just downsample and take only 10 to the 4th of these reviews to match with these reviews. Instead of resampling, we can use cost-sensitive learning. In cost-sensitive learning, we actually change the classifier, and we tell the classifier, even though this one, you've seen a lot more of this frequent thing, penalize it for misclassifying the really rare thing. And so that'll force it to focus a little more on the rare things than on the very frequent things. So 2 things you can do to deal with the imbalanced frequency problem that often occurs in real classes. We also, in our baseline algorithm, made the simplifying assumption that sentiment was a binary problem, positive or negative. So how do we deal with 5 stars or 7 stars or 10 stars? So there's 2 ways we can do this. We can map onto a binary class, we can say things that are more than 3.5 stars are positive or less than 3.5 are negative, or we can take the average of all the data, we can z-score, we can do various ways of drawing a boundary between positive things and negative things. Or we can actually attack the 1 to 7 classification task directly by using linear or ordinal regression or specialized models like metric labeling that's used by Pang and Lee. So again, we can either downsample and just do binary classification, or we can use a more advanced method of classification that lets us predict an ordinal value or a real valued number. So in summary, sentiment generally modeled as a classification task, polarity often with binary, less often with some kind of ordinal or linear valued label, and negation, a very important feature to use. For lots of tasks, using all the words in naive Bayes seems to work well. For other tasks, using subsets of words may help, and we can either use hand-built polarity lexicons, or for tasks for which the polarity lexicons seem inappropriate, we can induce lexicons using semi-supervised learning from some hand-built seeds. Now remember that sentiment is really just one of many kinds of affective state. It's a kind of attitude classification, but there's lots of other kinds of affective state classification that come up in their computational problems that are very similar to sentiment analysis. So to look at some of them, for emotions, we might want to detect annoyed callers to some dialogue system. So it's detecting the emotion of annoyance, or detect confused or frustrated students in an online tutorial versus confident students. For longer term moods, we might want to find traumatized or depressed people, like writers of some blog or text. In conversations, we might want to detect if someone's friendly or unfriendly. In very long-term personality traits, we might want to detect extroverts or introverts for building dialogue systems that can communicate better with extroverts or introverts. And there's lots of research actually on all of these tasks. We'll just show you one of them, which is a task we've worked on here at Stanford, which is detection of friendliness. So friendly speakers use, it turns out, use collaborative conversational style. So we built classifiers that look at features like how often someone laughs, or how often they use negative emotional words, or how frequently they use phrases like "that's too bad" that indicate sympathy, or agreement, "I think so too." So the more friendly someone is, the more likely they are to use sympathetic words or agreement, or the less likely they are to use a hedge like kind of or sort of. And we've shown that these classifiers help we've looked at the task of detecting how friendly someone is or how flirtatious someone is in speed dates. And we found that these kind of features help in detecting friendliness. So simple lexical features like words and phrases, and where we have speech, speech features like prosody or pitch, all of these can help in detecting sentiment, simple polarity, and much more rich affective meaning of all sorts of kinds.
Okay, so that brings us to what we had as part of the sentiment analysis, where we have seen that what are lexicons, what is basically analyzing the sentiment, and sentiment is not only about giving a positive or a negative sentiment, but also extending to things like attitude, finding out like the emotion, finding the context of what people are trying to express, so on and so forth. All these are part of sentiment. We have seen what are the researches that have been done, and we have seen in some cases how, if we try to find out or try to model our own run our own algorithms using supervised learning problems or semi supervised learning, then how we can be benefited by using these algorithms like the Turney algorithm and so on. Right? So that brings us to the end of today's class as well. Do again let me know if you have any questions on whatever we have seen today. As part of the videos, I'm going to share the link of all the videos with you. Uh, and yeah, see you again on Friday. Okay, so have a good rest, everyone. If you have any questions, let me know. Otherwise, feel free to rest for the rest of the evening. Yeah. Good night.